All right, moving on to reaction number 4 here with halogenation. So this is going to be looking at adding 2 halogens, 2 bromines or 2 chlorines. So we could see Br2Cl2 can also be used to add across that double bond. And so when we're looking at this reaction, again, we are going to see anti-addition. And so one of the things that we saw prior to this with anti-addition was the oxymercuration with that bridged mercury ion intermediate. Bromine does the exact same thing. And so just like in oxymercuration, what we get is anti-addition. We'll get 2 products, but they will be enantiomers to each other, with the bromines being added opposite, anti, one wedged, one dashed, and then the enantiomer. And so this will be anti-addition. We'll see the bridged intermediate in just a second when we do the mechanism. This isn't, technically this reaction is not regioselective, right? This is stereoselective. It's not regioselective technically because we're adding 2 identical groups. Once we start changing up a little bit with halohydrogen formation, we'll see that there is some regioselectivity here. But with 2 identical bromines, we cannot see the regioselectivity. All right, so let's write out that diatomic halogen. And what's really important here again to note is that this is our electrophile. But bromines, like chlorines, are high in electronegativity in terms of they have a lot of lone pairs. So when our pi bond goes and attacks a bromine, we do have a nuke attack with the loss of a leaving group here. But something unique happens as well with these 2 curved arrow mechanisms. Bromine is so large, same with chlorine, these halogens are so large, what actually happens is a 3rd arrow where we have back bonding occur. And so we make that bridged intermediate just like the mercury was. And so that bromine can appear as it's going to be a positively charged bromine. This is called a bridged halonium intermediate or bridged brominium intermediate. And this is really where that bridge allows us to see anti-addition. So because the bromine is bridged on the top side, it can be bridged on either the top or the bottom, right? Because the pi bond itself in the original reactant is trigonal planar. It has a top and a bottom side. That's where we can think about that second bromine coming in, and it has to come in opposite, backside attack. Think about that SN2 reaction coming in together. It's not a perfect SN2 reaction, but it's still a general substitution. And so either way, if we had bromine coming in on the first molecule where it has to be coming in from the bottom, if that bridge is on the top, on the wedge. Same thing for the second, that Br minus has to come in from the opposite side of the bridge. And so this is where we get 2 products that are enantiomers. And they will both be anti-addition. So it's a good thing to start remembering that bridge again from oxymercuration, seeing that there is steric hindrance on the same side as the bridge. So we have to have an anti-addition with that 3rd nuke attack and loss of leaving group. Just in case a perspective or a wedge and dash bond line structure doesn't do it for you, the textbook does have a really good diagram with the Hayworth projections. These would not be necessary for you to draw, but just in case you wanted to see how that back bonding occurs when we have the nuke attack, the loss of the leaving group, and the back bonding, right? So that alkene is the nucleophile, but again, that bromine is so big and has extra electrons that it actually sits right in between that carbon-carbon and makes that three-membered ring, that bridged intermediate. And that's a good thing to remember because that bridged intermediate means that there will be no carbocation rearrangements. And so we will see that in that second process of Br attacking that bridge, it has to come in from the opposite side, right? So this nucleophilic attack is the opposite side, here shown as the bridge on top and the bromine nucleophile, the bromide ion attacking from the bottom. Changing it up just a little bit, halohydrin formation. This is usually when we have something like water or another polar protic solvent in this reaction. We do the same exact first step, but what's really important to note with this one is that we get a different functional group at the end of the day. We'll get two sigma bonds to form, but notice how they are not both halogens. One is a halogen on the less substituted side, and the other one is an alcohol group on the more substituted side. So this is a regioselective reaction. It will happen in the same way as our halogenation. That's why we're kind of pushing reaction 4 and 5 together. Regioselective, the alcohol is on the more substituted carbon. And it is, again, stereoselective. We'll see that bridged intermediate anti-addition occurs. Let's go ahead and walk through this mechanism and we'll see a very similar mechanism of what we just saw with our halogenation. I'm going to draw out our electrophile, which is our diatomic. Br2 or Cl2 can be used in this. Pi bond breaks, attacks the electrophile, kicks off that leaving group, back bonding occurs. It doesn't matter which carbon you point that back bonding arrow towards, just point it back to one of them, one of the two carbons in that double bond. So here's what I want to draw, and I want to try to draw it as clean as possible here. To get the stereochemistry correct, we have our bridged bromine, and what it does is it pushes the rest of the carbon groups into a tetrahedral format. Notice that we're changing both the stereochemistry hybridization of both carbons in this first step. Both carbons of the carbon-carbon double bond are being changed to sp3 hybridized, and so we'll institute those wedges and dashes accordingly. So the bridged intermediate can be either on the top or on the bottom. I like to draw out both just so that we can see that setup right there. Now here's what we have at our disposal, Br minus or H2O. Let's think about who is the better base. We talked about this before in chapter 7 when we were discussing the leaving groups. Let's just remember here as a conjugate base, we can compare Br minus and H2O. ARIA is not the best thing to do. What is the best thing is to look at the pKa's. HBr has a pKa of -9. H3O plus has a pKa of -1.7. This is the most reactive acid, HBr. That is the smallest number. So if that is the most reactive acid, that means that the conjugate base is the most stable. And so that's where we see in this reaction, once we throw water into the solution, Br minus does not react. H2O comes in and it will attack the more substituted center. This reaction is as somewhere between an SN2 and an SN1. Water is a weak nucleophile, right? So remember, water did SN1 reactions. We do not see a carbocation intermediate occur because we only see anti-addition. But what's really important then is that this reaction is somewhere in between an SN2 and an SN1 as we start to think about that oxygen in water attacking one of these two carbons, carbon number 1 or carbon number 2. We will always see water attacking the more substituted side because that is the side that actually would be more stable, suitable to hold a carbocation. And so we get a regioselective reaction here that's very, very interesting. I'm going to draw out that last hydrogen just so that we can make sure our chiral centers are going to be correct here. If water is attacking from the bottom, it pushes and inverts that stereochemistry of carbon number 2. Right? Beautiful. Same thing can happen on this side. We'll get another H2O. Water is going to attack that more substituted center in an SN2 fashion, even though it's tertiary, it's somewhere in between an SN2 and an SN1, but there is a backside attack. The reason why a backside attack can happen here is primarily because we have a reactive bridged intermediate, right? We did not have that before in our reactions with chapter 7 and our SN2 reactions. So what's important to note here is why this is a tertiary carbon that's really reacting in a concerted style nuke attack and loss of a leaving group is because it's a different type of electrophile. It's a bridged 3-membered ring, which is highly reactive. All right, so we still see anti-addition, right? And we do see regioselectivity here. The last little bit is going to be that water cleanup step. I'm going to show it for one. It's a little proton transfer so that we can have our alcohol be neutral. I want to switch my groups on here for a second there. All right, so we do make enantiomers, right? What we'll see is that these are anti-addition products. We don't make all chiral centers. We have 2 chiral centers at the end of the day, but we don't make all stereoisomers. We just make 2 enantiomers. Excellent. Halohydrin formation, again, is very, very similar to our halogenation. So thinking about reaction 4 and 5, it's the exact same thing. The only difference is when you add water. You react water faster than Br minus or Cl minus. Same thing goes for that. And there's the mechanism. All right. There's again, the perspective Haworth projection if you wanted to see that anti-addition. Water is the better nucleophile. It attacks in an SN2 process with the anti-addition backside attack. But again, it's slow, so it will always attack the more substituted. So SN1 influence there. H2O attacks most substituted carbon. Now, dihydroxylation, doing 2 additions of OH. The first reaction that we have is, it's called epoxidation followed by ring opening. Now, MCPDA, meta, chloro, peroxy, benzoic acid. So when we're seeing this reagent, really that's just the acronym that is most often used. What we actually need for this reaction to happen is a peroxy acid. And so a peroxy acid is going to look like a peroxide double bond or two oxygens single bonded together, and a carboxylic acid decided to fall in love and have a baby. Watch this. This is a really, really crazy cool reagent. There's the peroxide, right? And it does look like a carboxylic acid. So it's called a peroxy acid. I highlight that peroxide bond because peroxides are very reactive, and that is the most reactive portion of this um, molecule. This will, again, be anti-addition, as we can see in those products. That is a stereoselective reaction. The intermediate, after step number 1, we are going to be making an epoxide. This makes that bridged oxygen. And that's what our functional group, what we are going to call the epoxide. And so that epoxide is an isolated functional group. You don't need to do a subsequent step after forming that epoxide. That can be the end of the day story. But for us, we're understanding what happens when we had 2 different sigma bonds across that double bond. And so we follow it up with a acid workup. And that is going to help us see where those 2 oxygens come into play. Now this reaction is a little bit intense, so let's follow it through and I'm going to highlight it. I like to bring this out from the textbook because this reaction has a lot of arrows going on with it all at once. The alkene, again, is the nucleophile, and it's going to attack that most reactive oxygen. The most reactive oxygen is the one that has the peroxide bond and the acidic hydrogen bond. And so that's where we see that first arrow coming into play. Second arrow is that peroxide bond is the weakest, and so that breaks to form an oxygen to carbon double bond. It causes the pi bond already in the molecule to break and to pick up that hydrogen. Look at that transition. It's that transition state shows that 5-membered ring transition state. That shows a lot of stability and a lot of locations of these atoms. What that causes is it causes the oxygen that was the original electrophile to go into back bonding. And so take a minute to really understand how this transition state is not only abstracting that oxygen that's most reactive from the molecule. What we end up making is a carboxylic acid with an epoxide. This is step number 1, what that peroxy acid would do. This could be the end for you. This could be that final functional group that you wanted to form. Epoxides are great. It's that epoxide thing that you can think about with a real life application with polymers and glue that you can get at the store. They call it epoxide because that's what the functional group is. The second step, the acid catalyzed ring opening of the epoxide, is where we start to see a very similar reaction. Look at it in almost the exact same way as what we would have seen with that bridged halonium intermediate or with our oxymercuration, right? We have a bridged functional group, and that is a reactive functional group. The only difference is that we'll start here with the acid catalyzed ring opening with a true catalytic step. We will use the acid to protonate our alcohol, or our oxygen, excuse me, of the epoxide. That makes oxygen a better leaving group. And so when we think about O- leaving, that's not good, that's a base. We actually want to see oxygen leaving as a neutral thing like water or an alcohol. And so we'll first do that proton transfer. H3O plus provides the proton. And there it is. That makes oxygen a much better leaving group. Water can then come in anti-addition, right? Nucleophilic attack. Beautiful. And then the last little proton transfer is just to make sure that we get 2 alcohol groups. So that first oxygen is from the actual epoxide. The second oxygen is from the water coming in. So we can see how that anti-addition occurs. We don't usually call this reaction stereo or regioselective because, again, we're adding two identical groups, but it is stereoselective. We can see anti-addition only occurs.